Welcome, everybody. I'm Katrin Heitmann from Argonne National Lab. I'm a computational scientist slash cosmologist. I'm going to talk to you tonight about the dark universe in which we all live. I want to give you, this talk has 3 parts to it. By the way, is everybody excited about I/O after today's sessions? Yay, I/O. It's actually one thing, I will not talk about it, but which has been a nightmare throughout my career. Anyway, I'm going to do this talk in 3 pieces. So the first one is I give you a very short introduction to cosmology and the dark universe and why we have put in so much effort to work on our code. The second part is a little bit of the HACC story, and this is kind of almost my life story. So HACC stands for Hardware Hybrid Accelerated Cosmology Code. And the name HACC actually describes the code pretty nicely. At Argonne, we have managers who say this is not a serious name. So they said it's HACC, but that just sounds silly. So it's really HACC. And if we have enough time, and I'm not getting too hungry because I'm only allowed to eat after I gave this talk, I will tell you a little bit about the science that we are doing with HACC. Before I start, I would like to thank the many collaborators who have contributed to this work. And the one thing that I would like to point out, actually, is that this is work that is done across multiple disciplines. So we have physicists, astrophysicists, computer scientists, statistics people. So that really makes this work very exciting for me because I get to talk to a lot of different people. And that makes it even more fun. So cosmology, in the way we are doing it today, is really a multidisciplinary science where we really need a lot of input from computer scientists to deal with the big data sets that we are collecting. We need very accurate simulations in order to analyze the data that we are collecting. And the statistics guys to help us actually interpreting what we get. Oh, and you were asking about the cosmic EMU. So this is something that we work together with the statisticians on. And it's like a trademark of our collaboration. So that's the Cosmic EMU. There's a web page to it. It's even, somebody picked it up and put it on a T-shirt who was not from our team. So that was a little weird, but there it is. So modern cosmology, how do we do cosmology? So cosmology is a little bit different from physics in the sense that in physics what we do is we build experiments and we focus into very specific things that we want to explore in the experiments, and we change our experiments to really get to the crux of the problem that we want to look at. In cosmology, we can't do that. We can't really build our own universe, or maybe we can if we have a very big supercomputer. And so what we do instead is we observe the universe. So we make maps, and we make maps in different wavelengths. And so what you see up here is 4 different maps. One is in the X-ray. One is in the microwave, one in the gamma ray, and one in the optical. So my talk will be mostly focusing on the optical. So what you do is you take these different measurements of the universe, you look at the statistics that you get from these maps, and you try to interpret that. And from that, you can learn a whole lot about the universe, and I tell you a little bit what you can learn. In order to interpret these maps, you need really, really large supercomputers. What you want to do is you want to make predictions, so you want to try and simulate the universe, and then compare your predictions to these maps and see if your theory is actually correct. So no cosmology without large-scale computing. Here I want to show you just an eye candy. This is from the Sloan Digital Sky Survey, which is a telescope in New Mexico. It's actually quite hot here. And it's a 2.5 meter telescope, and it was one of the very first big survey telescopes that mapped out the universe over a large area. So what you see here is basically a sea of galaxies. And what we are going to do now is we are going to zoom in on a very particular couple of galaxies. So you see all of these details in the survey. So we get the very large map that really collects all the data from this vast ocean of galaxies out in the universe. And we get the details of each of these galaxies as well. So when we do computational cosmology, what we want to do is we want to get the distribution of these galaxies right, but we also optimally would really like to get all these fine details right. So it's a very complex problem, as you can imagine. And just to give you a little bit of an idea about sizes, So the survey volume, if I look at an optical survey, is measured in something called gigaparsec. So 1 parsec is roughly 31 trillion kilometers. It's a little bit hard to imagine how much that is. But basically, when I'm talking about a survey, I'm talking about gigaparsec volumes. Another way how you can think about it is 12 billion light years in linear scale. The number of galaxies in these volumes is in the billions. So we can measure the images and spectra of billions of galaxies. And the typical intergalactic separation is a megaparsec. So you go from gigaparsec to megaparsec. And then you also want to look at the typical mass of a galaxy. So the galaxy has the mass that is in the light, in the stars. But it also has something that I will talk a little bit about in the next slide, the dark matter halo around it. So there's this big mass around a galaxy, and we can actually measure that mass, and that is roughly 10 to the 11 to 10 to the 13 solar masses. The typical galaxy size is in the 100 kiloparsec range. So what you should get from this slide is we talk about the observable universe, gigaparsec scale. We talk about the number of the separation of galaxies in the megaparsec scale. And the typical size of a galaxy is in the kiloparsec scale. So these are the orders of magnitude that you want to resolve in a simulation if you actually want to get a good picture of the universe. So what is the content of the universe? So by measuring these maps and interpreting these maps, we have learned actually quite a bit. What we have learned is that 95% of the universe is dark. What do I mean by that? I mean by that is that it has a dark energy component, so the matter energy content of the universe. 70% roughly is in something we call dark energy. So it's called, it was measured first in 1998 and got the Nobel Prize in 2011. And basically what you can imagine is if you throw a ball in the air, you would imagine that it comes down because of gravity. But what happens instead in an accelerating universe, this dark energy, what it does is it accelerates the ball into the air. So our universe is expanding ever faster. And that was actually a very surprising observation. So people thought, did not expect this. And so the question basically is, what is it? Why is it important now? If we would have lived 2 billion years earlier, we would not have seen this. So it's called the coincidence problem. Being totally ignorant and not knowing what it is, what we are trying right now in the field is to just characterize it better, making better measurements, understanding if there's something that gives us a hint, so that the theorist among us can actually say, okay, this is a cause for this. So this is one very big component of the universe. The other big component is what we call dark matter. So it's called dark matter because it does not emit or absorb light. And that is roughly 27% of the universe. So far, we have indirect detections. So if we look out in the universe, we see that light is bent around objects, which would not be bent if there's not a very big mass. We are trying with lots of experiments to actually capture the actual dark matter particle. We have not been successful so far, but we are hopeful at some point this will happen. It's kind of funny. Every 10 years, somebody will give a talk and say, we will find it in the next 10 years. And I'm now old enough that I can say, like, well, you said that 10 years ago already, and you didn't find it. But it's, it has to be there. We know indirectly it's there, and we just really want to figure out what is the particle that makes it. So this 95% dark universe is actually, I'm a theorist, and I'm very curious about it. What is the nature of these components? Where are they coming from? And in the simulation, that is actually what I'm mostly focused on, and you will see that. The observer's universe is the rest of the 5%, so it's the visible matter, and only 0.5% is in stars. So when I show you this survey of these galaxies, that's actually a very, very small component of the universe, but still it tells you a lot about this 95% of the dark component. So that's actually pretty exciting. We also understand the evolution of the universe relatively well by now. So we have a good picture about the initial conditions. We got that from the cosmic microwave background measurements. And so we have a theory how to evolve it forward. And what happens is that in the later part of the universe, so you see here like a time scale of the universe, very early on, the CMB epoch, 50 million years is, so you will see simulations of the universe later on. So 50 million years is roughly the age of the universe where we start these simulations. And then if you go forward, nonlinear structures form. You can't do pencil and paper calculations anymore, and you get this nonlinear structure formation, and galaxies form, and so on and so forth. So this is really where, again, large-scale computing becomes very, very important to resolve all of these structure formation questions. Another ingredient, if you want to simulate the universe, is you have to know what equations you have to put in. So the one thing that's really nice for us in cosmology is that gravity dominates on large scale. So what I can do is I can actually just make a simulation where gravity is the main force, and I can run this forward. I told you we know how to set up the initial conditions. It's a Gaussian random field with small fluctuations. And then I can put together an equation of motion that I want to solve for the dark matter tracer particles. We heard about the dark matter. So we put together tracer particles that follow the evolution of the universe. And then you put in physics. So for example, in these equations that you see here, that's the Bloss of Poisson equation that we have to solve. You have a dark matter component. So this omega total is a dark matter component. The omega lambda is a dark energy component. So you can put all of this into your simulations and start solving the equations. What you see down here in this box is actually a forward visualization of the simulation. So you start off with a relatively with a Gaussian field that has very small fluctuations. So you can see some spots that are slightly different color. What happens then is gravity starts acting on these. So they start forming clumps. And so you get forward in time, and then you see the structures that form today. What you should keep in mind when you see this is that I'm showing you here mostly the dark component of the universe. So what you see here is the simulation of the dark matter component with baryonic effects in it, but not too much, and a dark energy component that governs the evolution of the universe. Another thing that you notice is when you think about cosmology and the universe, you always hear the universe is expanding. So here you see in these movies that I will show you later on that the boxes always stay the same size. That's just a choice of coordinates. So we just take out the scaling to make it easier to do the simulations. A last point I want to make is that in 1996, Bob Dickey gave a lecture, and he said the universe is far too complicated a structure to be studied deductively, starting from initial conditions and solving the equations of motion. But this is exactly what we do today with these very large computers that we have at Argonne, Oak Ridge, and NERSC, and other places in the world. And that's really, really exciting. I mean, we have come a very long way. So just to recap, what do we have? We have the constituents that we need to put into our simulation. So we have the dark matter and the dark energy. We know what the dynamical rules are. We know that gravity is the dominating force, so we can put that in. We have an idea about the initial conditions. And fortunately for us, we have a very big supercomputer. So we can put this all together, and we can run a simulation. So what you see here is a simulation that we ran at Argonne. This is a 500 megaparsec box. Remember, I told you if I want a full visible universe, I need a few gigaparsec. But this one is a little bit smaller because we wanted a lot of resolution. So what you see now is that, so Z is something called redshift. It shows you the time. And Z of 0 is where we live, so you see this goes down. And so you see that the universe is actually starting to clump. So we are zooming into a region now. And so here we stop at a certain time. We just move around. But you see all of these structures forming. So we move on in time, and you see more and more things clump together. Gravity acts on things. And so now I can measure actually these structures. I can see how these structures are distributed. So now, being a theorist, I can change my universe. I can say, like, I don't know these constituents that I put in. Somebody told us about this dark energy. Maybe it's a fluke. Maybe it doesn't exist. What happens if I switch it off in the simulation and I just say everything is dark matter? I can do that. What you see here is a simulation. So the very first one is a standard model that I told you about. So it's the dark matter and the dark energy together. Then I said, OK, I want to switch off the dark energy completely. And what you see is that it's much more clumped. The colors, by the way, are velocities, but you can also think about them as densities. So the velocities and densities correlate. So what you see is you have many, many, many more small clumps. So if I measure the distribution of the clumpiness in the universe in these two and I compare them, I see they are different. And now I have to talk to my observer friends and ask them, okay, you are observing the galaxies, not the dark matter directly. How can we connect this? In the third one, I said, I don't like that dark matter is cold. I want to give it a little bit of a temperature. If I do that, again, things just look different in these structure formation pictures. So everything is washed out quite a bit. So really, these simulations give me, as a theorist, a very nice playground where I can switch the physics. What I can also do is change the initial conditions. I told you it's a Gaussian random field. I can make it slightly non-Gaussian. I can see what happens then. And so what the theoretical cosmologists do a lot is they are saying, OK, suppose something is different in our universe. Can I make a prediction for that with these pictures? OK? And obviously, I don't just visually look at them. I really measure things, right? I count how many clusters there are. I measure the clustering itself of the clumps and so on and so forth. So now I just told you I have to, unfortunately, go back and talk to the observers. As a theorist, talking to observers is difficult, to say a nice word. Because they think quite differently than I do. But anyway, so we have to do that because we actually want to test our predictions. We not only want to say, yes, if I have no dark energy, my clumping is different, but I want to test it against observations. So what you see here is like a cartoon of what we do. So I told you about the first two blocks, Titan and the dark matter distribution. And on the right, you see the Sloan Digital Sky Survey, from which you saw observations before. You also see Salman, who is sitting there in the audience, who looks very suspiciously at the telescope. He was not allowed to touch it. And so what we want to do now is we want to connect the dark matter distribution with the galaxy distribution. And so in order to do that, what we do is we go into the simulation, and we identify these very high density regions. So here's the zoom in. And so you see that there are these small high over density regions in the simulation. And we say that the galaxy, that the light roughly traces the mass. So our assumption is that wherever I have these very high over densities, I probably will have a galaxy. So this is a little bit cartoonish. The model is much more complicated. But if you do that, what you see in the middle plot, so in the middle plot, you see this red line is the density. So I measure the correlation function from the density. I measure the correlation function from the galaxies. So these are the black points with the arrow bars. And then I measure, if I populate the simulation with galaxies, how well I'm agreeing with the observations. And I find actually very good agreement. So if I would do the same now with these other two simulations that I showed you, I take the same model to populate it with the galaxies. This function will just go up much more steeply because the clustering is much higher in the model without dark energy. So this is how you can kind of verify that your theory actually makes sense. And the one very exciting thing is, so what you see there is the Sloan Digital Sky Survey image. And we are building right now the Large Synoptic Survey Telescope down in Chile. And this is a view of exactly the same field with a telescope that will have the resolution of LSST. And so what you see is that we get many, many, many more galaxies just because the telescope is 4 times as big. And so one thing that I will tell you a little bit about is how we want to model the distribution of the galaxies in the LSST survey. As you can imagine, I need much more resolution, so I need much bigger supercomputers, because you can see that if I don't capture the clumps at the resolution that I need, I will not capture the galaxies at the resolution that I need. So that's the big thing to do. OK, so now that we have a reason to get this very large simulation with very high resolution, we have to write a code that actually can do that for us. And so that's the hack code. And so I tell you a little bit the hack story, the story of the last decade of my life. When I said that the first time, I was thinking, wow, I'm getting old. But so the hack story actually started in the Southwest. And this is a picture of Roadrunner. And I'm going to talk quite a bit about Roadrunner. And it was the first machine to break the petaflop barrier. And So the story begins with an email. And sometimes an email can change your life. And I think this email actually did change our life in many ways. So Andrew White was, at the time, at Los Alamos National Lab in charge of supercomputing. Very smart guy, very big. He actually was a quarterback. And he sent us this email saying, what if you had a petaflop? And in 2007, nobody had a petaflop, so that was actually pretty exciting. So now probably this email would read, what if you have an exaflop, or even beyond that. And so the machine that Los Alamos was planning to get was called Roadrunner. And so it was the first machine that was supposed to achieve this petaflop performance. And it was supposed to achieve it via the so-called cell accelerators. So some of you remember the cell accelerators. Most of you probably have not heard of them because they came and went and were forgotten. But Roadrunner had these cell accelerators. And so Andrew White, or Andy White as he is known, was very smart in that he thought, like, if you have an architecture that is completely new, nobody has ever worked with such an architecture, you need some scientists who are actually willing to program this machine. And so at Los Alamos, the most important part of the lab are the weaponeers. The weaponeers are very rich, and they are not interested in like getting a machine that is not easy to program. So, but Andy White wanted to show that this machine is actually very, very useful. So he put out this call to everybody at Los Alamos and said, maybe there are some scientists who want to take on this challenge, get onto this machine and get some science from it. And so we looked at it. And so we said, this is a crazy architecture. Andy White said, no, it's not crazy, it's forward-looking. And he was right, absolutely right. And the one thing was clear, it needed a major code rewrite or a new code overall. And as I said before, Roadrunner probably was one of a kind. So it was clear at that time already that the cell was kind of like probably not going to survive. So what you wanted to do was to put together a code that's actually portable for future architectures. You didn't want to write something and then throw it away because this machine had a finite lifetime. So cosmologists are poor. You can see that. I have to give a talk to get food. And so we took on this challenge. I mean, for us, it was very exciting. Getting this access to the largest supercomputer in the world at that time was really, really cool. So what we did was we wrote something that is called MC3, mesh-based cosmology on the cell. It was based on something called MC2, which was actually a high-performance Fortran code. So Hack doesn't look like this much at all anymore. And later on, MC3 became Hack. So one thing that I thought was really nice, so as you can tell by now, my accent is German. And so every morning, I read the Süddeutsche, which is a German newspaper. And it was the first time that actually something was in the newspaper that I could send to my mother and say, look, I'm working on this. So I was really, really very excited. And I just want to highlight a couple of things for you. So the first one is, the first sentence is, ist der schnellste Rechner der Welt, which is translated, he is the fastest calculator in the world. And the interesting thing is that in German we have genders for everything. So supercomputers are male. So if I curse supercomputers, which I do on a regular basis, it's much easier to curse them when they are male than if they were female, for me. Another thing I want to point out is that my American colleagues always make fun of us Germans because we have these humongously long words. And so there's one word here, which is Atombombenexplosion, and you can all guess what that means. What it also said was, so there's cosmology, so you can see that. It's written with a K and an IE at the end, but almost immediately you can see what it means. And the supercomputer that leads by example, and technology of the future. So they were very excited about it. And again, I think they were kind of right that this was an important step into the future. And so here we started thinking. And so for computational scientists, it's really like, it's a crazy architecture. What do? We can't rewrite our code every time a new architecture comes along. And the computer scientists are super excited. So I wrote this slide actually a long time ago, but I already said exascale hybrid. Anyway, so you can see we started thinking, and they didn't want to hear that this might be a big challenge for us. And this is how Roadrunner looked like. And I'll go through this pretty quickly since this is a dinner talk and you should enjoy your dinner. So Roadrunner basically has these two layers. So the bluish dark purple one is the Opteron layer in this case for Roadrunner. It has 5% of the total compute, or it had, the machine doesn't live anymore. But it had half the memory, and it had balanced communication. So that was the part that everybody knew and loved in supercomputing world. Then the pink guys were the cells. So the cells dominated the computing. The machine was roughly 50 to 100 times out of balance. And so you can see it's very similar to the GPU machines these days, right? The architecture is kind of very similar. And so the biggest problem for us was that if you are calculating on the first set of cells up there, and you are talking, you can talk to the Opteron pretty easily, but you can't talk easily to the next set of cell accelerators. So you have to go through the Opteron layer, you have to go back up. So communication in this case is just difficult. So you want to avoid this as much as possible. And again, this is kind of true also for the GPU systems today. And the other thing that was a challenge was that the cells had their own programming language. And so as I said, we knew that this machine would not survive for us too long, so we didn't want to put in a lot of time and effort to write the part that lived on the cells. So it had to be an easy algorithm, as easy as possible, so that somebody could write this in a couple, maybe not a couple of weeks, but in a month or something like that. And then we could take it when the next architecture comes along, rip it out, and replace it by something else. So that was the idea behind this machine. So just to summarize these challenges one more time, so the Opterons had half the memory of the machine, balanced communication, but not much compute, standard programming paradigm C, C++, MPI, and the cells have the other half of the memory, but very slow communication, but 95% of the computing power. And a new language is required. So what we needed was a code that took care of the distributed memory, and gives the cells lots of work to do and make sure that the cell is easy to code so that if you have to replace it later on, it's easy to do that. And this is Hack in a nutshell. And again, I'm not going to spend too much time on this. There's a paper up there where you can actually look at details. But basically, the idea is that you see the Hack top layer where you see the decomposition on the Opterons in this case, where you have large chunks of the universe, so you see 50 megaparsec roughly. And this is where you have a long-range solver. So this long-range solver is a very large FFT, very large fast Fourier transform, as large as you can get. And since the Opteron communication is good, this actually worked quite nicely. Then what you want to do is you want to have a node-level solver that takes care of the very small scales. So in this case, what we did was we wanted the most easiest algorithm to implement. We just took an n-squared problem. So we took an n-squared solver. It was centered on the node, so it would not go between the nodes. And how did we do that? We did that via these overload boundaries that you see here. So basically, you knew what was happening on the other nodes in a little shell around you. So that would help you to know how your short-range solver should evolve. And this is how you have really a way that your algorithmic implementation is really focused on the node level. So the FFT, the big FFT that lives across the full machine, never changes when we move the code from one machine to the next. But the short-range solver changes depending on the architecture. So if you take the short-range solver from the cell and put it on a GPU, you rewrite it in CUDA if you want. OpenCL would work as well. So this was a very, very important part of the code. So we implemented all of this. We also implemented custom I/O, which took actually quite a bit of time. I can tell you after the talk why it was custom I/O and not HDF5. And so we did all of this. And here you see the result on September 24th, 2008. And you see a person there on the phone because the machine at Los Alamos was actually what is called behind the fence. So I could not go and talk to the people who ran the machine directly. So I would be on the phone, and it was actually kind of weird. So we would submit a job, the machine would start running. If you ever run on a very new machine, brand new machine, something bad always happens. So one node would go down, I would tell them on the phone, no, it didn't work, let's try this again. And so after some time, a lot of work, great help from the Los Alamos folks, you see that, yes, we were running actually on 99.77% of the machine. So that was actually very, very exciting. What you see also here in this little box on the left is that actually the opterons helped us to improve the performance of the short-range solver by 2 orders of magnitude. So a lot of speed up. So we could have never done on just the opteron level what we could do on the full machine. This is just to show. We compared it against other codes to make sure everything was good. So Gadget 2 is a standard code in the community. So it agreed with us to 0.5%. So that's very comforting. And so the Roadrunner story had a good ending. We had a code. Everything was good. And then Argonne called us up. And so they said, how about running this code on Mira? So Mira is quite different from what I just explained to you. So Mira is a blue gene queue system, and it gets its performance completely different. So it doesn't have accelerators. Instead, it has lots and lots of cores. So actually, not only did we start running on Mira, but we also moved our whole team to Argonne. So that was quite an adventure. And so the BGQ at Argonne is a 10 petaflop system. It's still there. BGQ at Sequoia at Livermore was twice as large. And so the new challenge is that we don't have accelerators anymore, but instead we have many, many cores. So the one thing was that we had to change our FFT a little bit, but that was pretty much straightforward. But then, as I said, what we did was we ripped out the short-range solver that we had developed for Roadrunner and completely replaced it with a different algorithm. So we decided the tree algorithm in this case was much better than a direct n-squared algorithm. And we did that, we implemented that. And so what you see up there in the corner is part of the hack team actually preparing for the Gordon Bell submission. And we achieved 70% of peak on the BGQ. So that was really, really exciting. So we submitted this, we made it to the Gordon Bell finalist list. But I want to show you here with this is that in a relatively short amount of time, because we had thought really, really hard how to design the code, we were able to port it to a new machine. It was not like the same code. There was a little bit of tuning. But roughly 5% of the code has to be ripped out and replaced by something else. So it's not that bad. And then we moved on, and Titan came along. And Titan was much more close to the Roadrunner architecture. So actually, what I didn't mention was that already in 2010, we had a GPU version of the code, but no GPU machine. That version was written in OpenCL. Titan actually preferred CUDA. So at some point, kicking and streaming, we took the OpenCL code and converted it to CUDA. And again, so one person took over this short-range solver business. We ripped out the short-range solver that we had now for the BGQ, replaced it with something else. We also added a new load balancing scheme, which is fine. And now we have a code that runs on the GPU systems. We again tried it for Gordon Bell finalists. Now I'm on the committee for the Gordon Bell Prize. So I'm like thinking, maybe I can do something now that we finally might win it. But anyway, so it again made it to the finalist round. It got very good performance on Titan. And now we are running on Summit really, really well. So then we again moved now to a new architecture, which is the Knight's Landing architecture. So Corey and Theta came along, and oops, that was too fast. And we kind of got bored just taking out the short-range solver, replacing it, running yet another simulation. We did that. It worked pretty well. Actually, within 1 day, so we started from the BGQ version of the code, which is very similar. Within 1 day, we had a KNL version of the code running up and working. So that was really, really good. But we thought, like, we can't have the same thing all the time. So we actually added new physics to the code. So now what you see here is actually we came a little bit closer to the observers. So we added the baryons to the simulation explicitly. And the new code, so the hack name was actually up to me, but the crack hack name is up to one of our students who is now a postdoc with us. So crack hack also doesn't sound very very serious, but it's actually a really, really nice code. And I just want to show you one thing. I don't want to go through the physics that we implemented. That would be another talk. But here's a nice movie made by J.D. Emberson. So this is actually the Borg simulation that was done on theta. And so what you see here is actually the baryonic temperature. And so the white part is the density of the baryons. You don't see it yet, but you'll see very, very soon. So now you actually really see what we see out there in the universe. You see the gas. So new physics in the code, still pretty portable. So that's rather exciting. And then we moved one more time back to Oak Ridge and to Summit. And yeah, I still have a little bit of time. So I can tell you, well, first of all, we went from 1 petaflop in 2008 to 200 petaflops in 2018. And I probably should have something to 1 exaflop in 2021, but I don't have that there but it will happen. We are all confident. And so one very short story on Summit is that, so what I didn't emphasize quite is that on each of these machines, we were kind of among the first users. So we were the first users on Roadrunner, the first users on Mira, the first users on Titan, and actually the first users on Theta as well, and on Summit. So on December 22nd, just before Christmas break, I got another email that didn't really change my life, but was important, from Oak Ridge saying, would you be willing to run they knew that the code was running on the machine quite nicely, but they wanted to have somebody to stress test the full machine. And they didn't have apparently that many codes that can run on the full machine. So they said, would you be willing, even though it's almost Christmas break, to run the code on the full machine? You will be the only user. And I said, wow, this is cool. And there is a file system, which is also not always true when a machine is just brand new. That was one problem that I didn't mention with Mira, that at the start there wasn't a file system, so it was not so cool to run. So they had a file system, a machine, and nobody else during the Christmas break wanted to run on this machine. So I asked them, am I allowed to write out some data? And they just said, yeah, sure, write out some data. I wrote out 8 petabytes of data. We ran 3 simulations, each involving almost 2 trillion particles. These are like the biggest simulations right now worldwide available over the Christmas break. So that was really, really cool. And the one thing with I/O I have to say is, if I have the machine for myself, it's much easier. It's these other people who disturb my I/O with their file system hammering. And so that worked really, really well. So we are analyzing these simulations right now. And that's fun. Here's just hack in pictures. So for Mira, actually, the team together with ALCF folks got the Directors Awards because we really stress tested the machine a lot when it has just arrived. Then you see us there preparing for the Gordon Bell paper. And down here, you see a picture of Gordon Bell and all previous finalists. So I'm there in the back. And the one very sad thing is that I'm the only woman in this picture. And every time I show this picture, I say, we will change this. There will be more women in the future who are part of the Gordon Bell finalist photos. So just a small movie. So we started with MC2, which is really, it's a very nice code, high-performance Fortran. A little slow, but there it is. And it only runs on very specific machines these days. And then we have Hack, which really is very, very fast and can run on all of these different machines. So in the last 8 minutes that I have, right, roughly, I can tell you a little bit more about the hack science. So one thing that we can do with these simulations is we can ask fundamental physics questions. So I showed you that. We can change the ingredients of the universe. We can change the initial conditions. We kind of can play God. And so we can see what comes out of this. The other thing that we can do is we can develop new probes to understand the universe. Like, how can we measure the distribution of galaxies in different ways to actually get a better understanding of the universe? So we can try this all out in the simulations and then go to the observers and say, you should actually do your measurements like this. The other thing, and that's what I'm going to talk about a little bit more, is we can simulate full surveys. So we can really do simulations that have everything in them, and then use these simulations to prepare for real data. So I'm going to talk about this a little bit more. So this is the Large Synoptic Survey Telescope, how it looked like, I think 2 months ago. And it's a telescope that will be operating in Chile. It's an 8-meter Mira, and it will scan the night sky every 3 days, right? Every 3 nights, not days, of course. And so it will go on for 10 years. First light is hopefully next year. First science data will be coming out in 2022. And it will have lots of alerts every night, so things go boom in the night sky, and so the telescope will tell all astronomers around the world something weird happened in the universe, take a look with your telescope. So this is actually an interesting challenge also from the computer science perspective, like what do you follow up? So you have all the stuff going on, and you don't have infinite amount of telescope time to follow up. So how do you decide what to follow up and what not to follow up? So this is called, so-called brokers are written, where machine learning is playing an important role to decide, okay, this is worthwhile and this is not so interesting. We will also survey the sky, so we will measure almost 40 billion stars and galaxies. So that's the part where I am more interested in. And so the dark energy science collaboration, as the name says, we are focusing on the dark energy question, has formed. And we decided, since we have to wait for the real data, we simulate the survey as closely as possible as we can until the real data arrives. And so the dark energy science collaboration is an international collaboration with almost 1,000 members now, so quite a few people. And we decided to do this. So what you see here is, in red, the 18,000 square degrees of the southern sky that will be surveyed by the LSST. And there's something called deep drilling fields, which mostly means that the telescope will stare at that part of the sky for longer and longer. So the longer you stare, the more dim objects you actually capture. And there will be also some mini surveys where the community can actually say, we want to use this telescope to do something very specific. I told you about the worldwide alerts already, so they come out nightly. Minimal information, so it's really up to the astrophysicists to decide what to follow up and what not. And there are annual data releases that will come out. Those are more like the maps that I showed you at the start. And so LSST Desk decided to simulate a little piece of the survey, 300 square degrees, but to try to make it as realistic as possible. What you see here is the camera. So I'm showing this to you in order to make you understand a little bit more when I show you the simulation picture, how this actually connects. So the camera that you can see with this person there next to it, it's roughly, it's a little less than 2 meters in diameter. And inside the camera, what you see there is the focal plane. And so you see here a blow-up of the focal plane and the CCDs inside. And so we want to do a simulation including everything. So we want to simulate the universe, as I showed it to you before. We want to populate it with galaxies. We want to take each galaxy and trace their photons through the universe to us, through the atmosphere, hitting these CCDs. So that's what we set out to do. What you see there, oh yeah, I forgot to say that. What you see here on the right is actually the observing strategy of the telescope. So you saw this green patch on the previous slide, which is what we want to simulate. So that's the same green patch. The blue guy is one of these deep drilling fields that we want to simulate. And now you see how the telescope, with its focal plane, is hopping around trying to fill up this green patch. So this is all in our simulation. So we really have the observing strategy that the real telescope is planning to implement. And so what we'll do is we'll simulate these round patches of the sky and see if they look like what the telescope will see. This is kind of a cartoonish picture. So again, we start with the extragalactic catalog. So you have seen all, we do these very large simulations. So the simulation that we will use for this is actually a very big Mira run. We populate it with galaxies, given some model. Then we take each galaxy, we ask how many photons do you have? we do image simulation. So we really simulate how the image would look like that the telescope would see. In this, we have things like, so between the universe and us are the stars in the Milky Way. There's lots of dust. All of this is in here. We will also simulate the defects of the CCDs, like the telescope is not perfect. All of this is in here. After we have done all of this, we process it. So just like the real telescope data will be processed, we process it with the LSST science pipeline. So what that means is you do a calibration of the data, you clean it up, and hopefully you get something you can do cosmology with. So just very quickly, the three ingredients. The first one is the extragalactic catalog. So you have heard a lot about that. So this was a simulation carried out on 2/3 of Mira. Again, one of the largest simulations available right now. We populated it with galaxies. We then did a lot of validation that what we got was actually correct. And by comparing with actual data that is already available. And so the result was a catalog where we have galaxies, and each galaxy has more than 500 properties. So this one slide by itself will lead to 5 papers. 3 of them have been written, 2 of them are in preparation. So there's a lot of work, as you can imagine, in here. On the right, you see a picture of the halos in what is called the outer rim simulation, this Mira simulation that I was talking about. And you can see the 4 gigaparsec that we chose, so we can stuff the whole full survey in it. The second part is the image simulations. So the image simulations are rather costly, so you can see me here at Argonne actually looking at the activity of theta. And all of this is are our runs, so we used a large chunk of theta. We also did run on Curie at NERSC, a large chunk there. We put together a workflow to make this happen. And what you see here is a picture of the image simulation. And now hopefully you can remember that there was this picture of the LSST camera focal plane. And this is what you see here now. And what we have to do is we have to simulate 7.5 million sensor visits to get like a 300 square degree chunk for a 10-year survey. This is just to remind you how this all looks like. So you see there's this little CCD, and it has these little segments. And this is actually how the simulation looks like. So on the left, you see these little segments that you saw before. The white blobs are either stars or galaxies. And what you also see is, so this is the last step in this whole thing put together. What you see is the defects in the CCD. So maybe if you sit very far away, you can't see this, but you see there's these rings. So these rings are inaccuracies from the CCD measurements. You see these different colors, which have to be calibrated out. So you take image simulations also of the CCDs without any galaxies in there. So you do all of this, you clean it up, you run it through the LSST science pipeline, and you get a clean image. So we have done this. We have generated 5 years of the 300 square degrees. The science collaboration is looking at it right now. Unfortunately, they found a few hiccups, but we are working on that. But the whole pipeline is set up. We have done a 5-year survey so far. We can go on for a couple more years. We have enough allocation for that. And so we are actually able to do all of this. And so then when you put it together, this is how our simulated observed universe looks like, how LSST will see it. So this is actually an image that was generated from these simulations after all of these steps were done. And that's it. I'm ready to eat now. Thanks, everybody.